Thank you for for the detailed introduction, Dr. Yano. As introduced, I'm working in Virginia Tech now as a faculty member, but for today's talk, I'm going to present data obtained from my previous lab, Dr. Julia Berry's lab at UC Riverside. We have been working on molecular mechanism and also physiological mechanism which underline submergence tolerance in rice. We primarily focus on the function of SUB1A in rice. So first of all, I'd like to show the physiological function of SUB1A. As you may know, there is a very strong gene which increases submergence tolerance in rice called SUB1A. And using this slide, I'm going to show the effect of the gene. So there are 5 different rice cultivars here. They are all different genotypes. And the first genotype, this is LG japonica, and basically all japonica we tested lack SUB1A. And this is japonica LG genotype. It doesn't have SUB1A. And second, third genotype, these 2 lines are overexpression line of SUB1A. And the background genotype of these lines are LG. And fourth line, M202, this is also japonica. It lacks SUB1A like LG. Our last line, M202 sub1, this is near isogenic line of SUB1A. So it has SUB1A, but the background genotype is M202. And they are look similar. They are developmentally identical. And they are submerged for 16 days completely. And this is the picture after 16-day submergence. As you can see, japonica genotype, LG, M202 elongated, longer than other genotypes. This is a typical submergence response in rice. They attempt to escape from submergence. However, SUB1A containing genotype, transgenic and NIL, they restrict elongation. And we also continuously observe these genotypes under regular growth condition. So we observed recovery after 7 days under regular growth condition. So actually, recovery, suddenly oxygenation is also abiotic stress. It's another type of stress. So during recovery period, almost all LG plant and M202 plant, they died during recovery period. However, transgenic line and near-isogenic line, almost 100% of these plants produce vegetative tissue during recovery period. So this is the effect, physiological effect of SUB1A. SUB1A protect meristematic tissue, and after the stress, the tissue can reproduce. Tissue can produce vegetative tissue. One of our graduate students, Greg Body at UC Riverside, have done some metabolomics analysis using proton MMR technique. So this is one of example. First of all, he quantified sucrose content in leaves. They are submerged. As you can see, submergence decreases sucrose content in leaves. However, M202 sub1 maintained more sucrose as compared to M202. So this is one of the quiescence responses. SUB1A maintain carbohydrate such as sucrose in leaves. And he also quantified many amino acids which are related to glycolysis pathway and also TCA cycle. They are produced using intermediate of glycolysis and TCA cycle. And basically, these amino acids are accumulated in response to submergence, and M202 plants leaves contains these amino acids during submergence, and then the level drops upon desubmergence. So this is also one of the example of quiescence response. M202 sub1 more accumulated amino acid. So this data indicate carbon flow is slower in M202 sub1 than M202. So it's beneficial to avoid carbohydrate starvation during submergence. So SUB1 plant can endure complete submergence for a long time period by avoiding carbohydrate starvation. And we also examined whether or not SUB1A increased drought tolerance. This experiment has been done by another grad student at UC Riverside, Elaine Young, under my supervision. First of all, we compared published microarray data set, submergence induced gene versus dehydration-induced genes. Submergence drought, they are totally different water status, totally opposite status. They cannot occur at the same time, but they can occur sequentially. And interestingly, we found more than 25% of submergence-induced genes are also upregulated by dehydration. This is very big overlap. And we also compared SUB1A induced gene versus dehydration induced gene. And this is also pretty interesting result. More than 28% of SUB1A induced genes are also induced by dehydration. So this is also big overlap. And this indicates SUB1A may regulate dehydration induced gene as well. So to test the effect of SUB1A on dehydration stress tolerance, first of all, we grow M2 to M2 to SUB1 plant in a single pot. This is 2 weeks old seedling, so they are developmentally identical. And then we stop watering for 8 days to make a dehydration condition. Both genotypes are exposed to dehydration equally in a single pot. And then we water this plant and observe recovery after 14 days. As observed during and after submergence, we observe M2 to SUB1 produce new leaves during recovery period. So it seems the effect of SUB1A, which is protection of meristematic tissue, is conserved during submergence and also during dehydration. We also quantified water loss in leaves in M2 and M2 to SUB1 during dehydration. Water level dropped in leaves in both cell types, but at day 5 and day 6, M2 to SUB1 maintained more water as compared to M2 to leaves. So this indicates SUB1A slowed down water loss. And we also quantify MDA content. MDA is a good indicator of lipid peroxidation, which is induced by oxidative stress. MDA content increased by 12 in both genotypes, but M2 contained more MDA. So this indicates SUB1A also restrict lipid peroxidation during dehydration stress. ABA is a very important hormone which regulates many types of defense response, acclimation response to dehydration. Drought increased ABA level and accumulated ABA promote LEA protein accumulation. And ABA also regulates water loss by regulation of stomata closure. As a result, ABA confers drought tolerance. And we examined the responsiveness to ABA using Y-type and SUB1A overexpression lines. And ABA decreased seed germination. This is seed germination observation. We observed seed germination was restricted by ABA in all genotypes, all the 3 genotypes. However, in the SUB1A overexpression lines, the seed germination was more severely restricted by ABA. And this is shoot elongation data. Shoot elongation is also inhibited by ABA. And again, consistent with the seed germination, the transient lines, shoot elongation was more severely restricted, inhibited by ABA. So these 2 data indicate SUB1A increase responsiveness to ABA. And this is physiological observation, and we also did a molecular experiment. We selected ABA in these proteins. All of them are highly induced by ABA, and also they are all dehydration-induced proteins. And interestingly, even under marked condition, no ABA condition, we observed constitutive expression of these genes. So this indicates SUB1A acts upstream of these transcripts. And these are all very important genes which are related to dehydration tolerance in rice. An application of ABA increased transcript of these genes, and overexpression line contained more transcript of these genes. So this experiment confirmed SUB1A increased ABA responsiveness at mRNA accumulation level as well. And we also examined whether or not dehydration is associated with submergence or not. Now actually, dehydration is a part of submergence stress. To test that, we used 2 weeks old seedling. This is before submergence. They look very similar. And then we submerge this plant for 7 days. You see elongation response in M202. It's a typical response, escape response. And then we continuously observe these plants under regular growth condition. And actually, both plants are exposed to dehydration. It looks leaf were desiccated after this submergence. And this is brought up to picture. It's pretty obvious M202 leaves is more severely loaded as compared to M202 SUB1. And actually, this is also observed in the field condition. So it's a pretty common response upon submergence. And we also quantified water loss in leaves. As observed during dehydration, M202 SUB1 maintained more water upon the oxygenation. This also confirmed SUB1A blood water loss. We also visualize reactive oxygen species accumulation using 2 specific dyes. Upper leaves, upper 6 leaves, these are non-submergence control. And lower leaves, they are submerged and then desubmerged. As you can see, M202 has blue pigment, brown pigment accumulation. And blue pigment indicates superoxide anion accumulation. And brown one is hydrogen peroxide accumulation. So this indicates submergence, and desubmergence promote reactive oxygen species accumulation, such as superoxide and hydrogen peroxide. And this is quantitative data. We observed MDA content in leaves during and after submergence. Actually, we didn't see any effect of submergence in MDA content. But upon desubmergence, we observed accumulation of MDA, especially in M202, which is consistent with the observation during dehydration. This data suggests SUB1A block loss accumulation, which is beneficial for lipid peroxidation reduction during dehydration. I'd like to summarize data presented today. I didn't present this sequential response. I didn't have time, but this is already published. Submergence increase in the absence of SUB1A, rice plant use escape response. So in the absence of SUB1A, submergence increase ethylene production, accumulated ethylene increase gibberellic acid production, and responsiveness. It's pretty beneficial to increase shoot elongation and carbohydrate consumption, which is beneficial for escape strategy. They can escape from submergence by rapid elongation response. However, this strategy can be dangerous under deep water condition. They can be exposed to carbohydrate starvation underwater. So to avoid starvation, SUB1A plant use totally different strategy. in the presence of SUB1A, SUB1 plant use quiescence strategy. SUB1A is induced by ethylene, but SUB1A also block ethylene production by feedback regulation mechanism. Another function of SUB1A is blocking GA responsiveness, gibberellic acid responsiveness, through SLR1 and SLRL1 pathway. And these two pathways are beneficial to reduce shoot elongation and carbohydrate consumption, which is beneficial for quiescence response. They can economize carbohydrate reserves to avoid carbohydrate starvation. So using this strategy, they can survive, endure prolonged submergence for a long time. And submerged plant eventually is exposed to dehydration, deoxygenation, I mean. So sudden exposure to oxygen is one of abiotic stress, which is oxidative stress. And deoxygenation increase loss accumulation, but SUB1A reduce loss accumulation. And submerged water also is exposed to dehydration stress as observed. Dehydration also increases SUB1A, and SUB1A promote ABA responsiveness, which is beneficial to increase LDA protein accumulation, and it also block water loss. As a result, SUB1A confer multiple stress tolerance, including submergence, deoxygenation, and dehydration. And as I said, submergence, dehydration, these stresses are totally different, but they occur sequentially during and after submergence. So it's not surprising that a single gene confers multiple stress tolerance. We believe it's necessary component. Submerged tolerant plant has to have dehydration tolerance. And we also tested the effect of SUB1A on leaf senescence. Leaf senescence usually occurs at the end of leaf cycle. It's a developmental cycle. However, leaf senescence also occurs during submergence, dehydration, and other abiotic stress. So regulation of leaf senescence must be pretty important for abiotic stress tolerance. We used to prolong darkness, constant darkness, to stimulate leaf senescence. So these are 2 weeks of seedling M202, M201 pair and LG overexpression pair. These are exposed to prolonged darkness, constant darkness for 14 days. We observed chlorophyll degradation, leaf senescence, especially in M202 and LG. And this is a more longer time period, 18-day dark treatment. And then we move this plant to regular growth condition in the light. So as observed after submergence and dehydration, we also observe recovery, vigorous recovery from SUB1A containing genotypes after dark treatment. So it seems SUB1A's function is pretty conserved after submergence. And we also tested the effect of ethylene. First of all, we did dark treatment using leaf segment. So we floated leaf segment in MS media, and we put this plate under darkness for up to 9 days. So you see clear chlorophyll degradation, leaf senescence in M202. And this is dark plus ACC treatment experiment. ACC is an immediate precursor of ethylene. Addition of ACC can promote ethylene production in rice and other plant species. This experiment indicates addition of ACC promote, accelerate leaf senescence induced by darkness. So you see difference between the two at the same time point. However, this is M2 sub1 darkness. This is M2 sub1 dark plus ACC. We don't see any obvious visual difference within the food. This indicates SUB1A decrease the effect of ACC. We also quantify ethylene production during darkness. Constant darkness promotes ethylene production. However, mTOR SUB1 and SUB1A overexpression line replaced ethylene production induced during darkness. And we also observe this phenomena during submergence. Submergence also increases ethylene, but it's reduced by SUB1A. So this data indicate SUB1A block ethylene process. Methyljasmonate and jasmonate, this is a very important hormone which promote leaf senescence, and we examined the responsiveness to methyljasmonate using wild type and SUB1A overexpression line. This hormone actually reduced shoot elongation in rice and other plants, and we compared inhibition of shoot elongation by this hormone. As you can see, wild plant is more severely reduced by this hormone. This indicates SUB1A reduced responsiveness to this hormone. We also did a molecular experiment. We selected 3 genes which are induced by this hormone, methyljasmonate. And again, these genes are highly induced by the hormone, methyljasmonate. However, in the transgenic line, the accumulation was reduced. So this molecular experiment are also upper panel physiological experiment. Both of them indicate SUB1A blocks methyljasmonate responsiveness. And we also tested the effect of methyljasmonate on leaf senescence. The hormone application of this hormone decreased chlorophyll content in algae, especially in algae. And this is methyljasmonate plus ACC experiment. Addition of ACC promoted leaf senescence induced by methyljasmonate. So you see some difference between this and this at the same time point in algae. However, we don't see any obvious effect of addition of ACC. So this experiment also confirmed SUB1A reduced the effect of ACC. This experiment indicates SUB1A block ethylene production, which reduce methyljasmonate responsiveness, which must be beneficial to delay leaf senescence during darkness. So this is summary. We have 2 summary. First summary is SUB1A can enhance multiple stress tolerance, including submergence, deoxygenation, and dehydration. And all of them can occur sequentially during and after submergence. And second conclusion, SUB1A can delay leaf senescence induced by prolonged darkness. And we believe this mechanism must be very important for submergence tolerance and also dehydration tolerance as well. Lastly, I'd like to thank all people involved in this project. As introduced, I worked in the laboratory of Julia Berry's lab at UC Riverside. And Professor Cindy Lee and her student, Greg Pauling, they have done metabolomics analysis using my submerged plant. And Elaine Yang is an undergraduate student who worked with me at UC Riverside. And we have other collaborators in other institutes, Dr. Pam Ronald, Kenon Chu, and David McKell. They have done initial mapping work and map-based cloning. That's very time-consuming process at that time. And also, David McKell and Abdel Ismail, they have done many weaving work and also some physiological analysis using SUB1A plants. This work has been funded by 2 U.S. Funding agencies, USDA and National Science Foundation in the U.S. And lastly, I'm looking for a postdoc and a graduate student in my lab. And I'm still continuing this submergence research in rice. So if you are interested in this topic and in my lab, please let me know. Thank you.
Thank you very much for Dr. Fukao for the excellent presentation. So this presentation is now open to discussion. Yeah.
You mentioned that SUB1A affects ABA responsiveness. The ABA signaling pathway is very well understood now. Do you know which step in the process is affected by SUB1A?
Well, we haven't tested. Right, there is a very useful mutant collection in terms of ABA, but we haven't tested, and we don't know which one is a direct target of SUB1A. Yeah, it's a very useful.
Pretty straight, simple experiment to do.
Yeah, if we have mutants.
You don't have to use mutants. The molecular process is very well understood. There are marker proteins, marker transcription factors to be tested.
Yeah, we can observe mRNA accumulation. Right.
Okay. My question is, in our breeding program, we already tested, because the original SUB1A is from the FR13A, right? And we found this variety extremely sensitive to drought. It's most extremely sensitive to drought. So that's the one thing is suggesting the association of SUB1A with the drought tolerance under field conditions remain to be tested. Second question is, when we are doing the integration breeding in our drought select progeny, using FR13A, we found all drought selected progeny, SUB1A was completely eliminated. That means no expression for the SUB1 region, SUB1A region. So that also suggests the SUB1A may not really associate with drought on the field condition. I'm not sure if you can elaborate any interpretation of this data.
Okay, so right. FR13A is a source of SUB1A, but FR13A contains many genes other than SUB1A. Some of them can increase dehydration tolerance, but some of them can reduce dehydration tolerance. And a mixture of these genes can determine dehydration tolerance in the genotype. So I don't think we can conclude SUB1A cannot increase dehydration tolerance. Based on our research used the near isolate line, so it's a very useful system to see the gene function of the single gene. And you haven't done a field test yet, so we understand the importance of field test to determine the function of the gene.
Any other question?
What would be your thought about stagnant flash flooding?
Second, what?
With SUB1A. And if you have a situation where you have stagnant flash flooding, like it happened last year in Thailand, the water stayed for a month. SUB1A would just stay in the water.
Right. Yeah, that's a different kind of submergence storage. SUB1 works very well only for transient submergence. So to function SUB1A, water level have to reduce quickly. If water level is still remained, actually SUB1A has a negative effect on rice. So we need some additional gene to make a more tolerant, submergence tolerant rice cultivars. And our lab and other labs are also working to identify a useful gene to complement submergence tolerance rice.
Any other? So let me ask one question. So multiple tolerance, SUB1A induced multiple tolerance of multiple stress, right?
Tolerance for?
SUB1 induce the tolerance of the to the multiple stress.
Right.
So, such as multiple induction occurred alone or some conjunction with some submergence stress and then dehydration tolerance. I just want to be clear that only one stress, for example, in the drought stress, can be inducible by SUB1A.
Yeah, only dehydration increase SUB1A mRNA accumulation.
Yeah.
So it's not necessarily submergence.
Yeah.
Right. Submergence is not necessary to increase SUB1A mRNA level.
Okay, I see.
Right.
Another question? So if no, so thanks again for the Dr. Fukao for the presentation. I would like to close the early session of this morning and